We're going to expand a little bit on the idea of these forces and resultant forces and vectors and do a little bit of an example where we have charges in equilibrium. Okay, so in the last video I did a superposition example where you had multiple charges and we just wanted to figure out what the net force on one specific charge was. Okay, so we can actually have charges in equilibrium, right? So if I put let me just give like a basic example, right? If I put a charge here and a negative charge here and a negative charge here, and we had some distance x, let's just say it's like a half a meter or something, and this was a half a meter, and both of these two negative charges were the same. Let's say they were 1 microcoulomb and 1 microcoulomb, okay? So this charge is attracted in this direction by some force, and this charge is attracted in this direction as a result of that one, right? And because the magnitude and the distances are the same, then we would say that this charge is at equilibrium, okay? And it's where the net force is 0. 0, or where F1 equals F2. Okay, so we're just going to do an example where we have this sort of situation, okay? So let's say we have a point charge that is, so now I'm going to do another one with like a little bit different numbers. So I have a positive charge here and it's 2 microcoulombs, so plus 2 microcoulombs. And over here I have a negative charge and it's 0.2 meters away and it's negative 3 microcoulombs. Okay? Now the question is, where would I place a charge that is negative 4 microcoulombs so that this charge is in equilibrium? So where would I put, let me see, where do I want to write this up here? I'll just write it right here. Where do I put a 4 microcoulomb, and it's a negative 4 microcoulomb charge? So, so the net force is 0, or we're at equilibrium, right? So really it's going to be over here somewhere. And these two, it's a little bit stronger of a force than what this is going to exert because of the charge. So we're going to guess that it's probably going to have to be a little bit further away than 0.2 meters for them to be equivalent. So all we're going to do is we're going to set them equal to each other, right? So we're going to have a, we're going to say that the force of charge of this charge over here on this charge, so we'll say the force of charge 3 on charge 2, 3 on 2, and this might be kind of a cumbersome notation, but we'll get it, has got to be equal to the force of the 4 microcoulomb charge on the second one, so force of 4 on 2, okay? So we're just going to set up an equation. So this is force electric, so we got 9 times 10 to the 9th for Coulomb's constant, times, we got 3 times 10 to the negative 6. And again, I just kind of ignore these positive and negatives because that just tells me direction, which I can visually figure out a lot easier than, you know, trying to remember positive, negative, all that mess. So then we have 2 microcoulombs, oops, that should be negative 6 there, all divided by 0.2 squared, has to be equivalent to the force 9 times 10 to the 9th, and then we've got 4 times 10 to the negative 6 for the 4 microcoulomb charge that I'm going to place somewhere, times 2 times 10 to the negative 6, all divided by r squared. So that's what we're trying to solve for. Okay, so this times this divided by that actually gives me, let's see, 7.5 times 10 to the 5th. I've already done the calculation, so I can just make the video a little bit shorter. So 7 times 10 to the negative 5th is equal to, and then you get this times this times this, is actually 4 times 10 to the negative 6th. So 4 times 10 to the negative 6th, all over r squared. So then we're just going to solve for r, and actually get that r is equal to 0.23 meters, which makes sense. So that's what we predicted, right? Because if you've got a stronger charge, that's going to, you know, in itself make the force a little bit stronger. So in order for the forces to be equivalent on either side, it's got to be a little bit further away than these two charges are from each other.